So this is definition 1 in section 1.4. If A and B are n times n matrices, such that A times B is equal to B times A is equal to the identity, equal to 1, then let's start with this. B is called the inverse, oh God. The inverse matrix of A. We write B is equal to A inverse. Yeah, so this is really like for numbers. The only thing is we have to say it's from both sides. Turns out later on we will show this is not necessary. If you have only one side, it's okay. Just in the moment we don't know, so that will take a while. And so if the matrix A has an inverse matrix, then we call A invertible.
Does that say if A or B and B are n times n?
Matrices?
Yeah, does it say it's the same letter, n times n?
Yes.
Okay, thank you.
That's something that's important also. That's something I will say in a moment one more time. So n times n, and both of them have the same size, n times n. Huh? Okay, so if A has an inverse matrix, then we call A invertible. If A has no inverse matrix, then we call A singular or non-invertible. So we have an inverse matrix. Inverse matrices that have an inverse are called invertible, so there is an inverse. And matrices which have no inverse matrix called singular. Okay, so important, so just as a remark. Number 1, if A is not square, there is no inverse matrix. So inverse matrix exists only for square matrices. So A has to be a square matrix. To be invertible. No? If it's not square, you don't even need to check anything. Non-square matrices have no inverse. Second, this definition is totally symmetric. So here I have said B is the inverse matrix of A, and we say B is equal to A inverse, but you can also say that A is the inverse matrix of B, because the definition is totally symmetric. There's no special thing about A or B. No? So we can also say A is B inverse, no? Because this is just, I picked A as the first one, but it really doesn't matter. You can flip this definition, no? Is this clear until now?
Yes.
Okay, because then right away there's something what we also expect for real numbers, because A is also B inverse, but B inverse is A inverse. So an invertible matrix is the inverse of its inverse, no? like from 3 to go, you go to 1/3, and the inverse of 1/3 is 3 again. Yeah. Also, because it's symmetric, we have this, and therefore we have this. In the book, this is a result which comes up later in a separate statement, but it's already clear up here from the symmetry of the definition. Okay, before we move on, if you think about it, if you think about the regular numbers, the real numbers, which are 1-by-1 matrices, no? What is the only number which has no inverse for the real numbers?
0.
Yeah. So only for the real numbers, only the 0 has no number that I can multiply to get a 1. No? Okay, so what we expect for sure is the 0 matrix should have no inverse. No, I mean, that already fails in one dimension. No? And it turns out for matrices, it's more complicated. And that's something which comes up now in our first example. So again, keep in mind, the definition is, if you like to find an inverse for A, you have to find a matrix B such that AB is equal to BA is equal to the identity. Yeah. So our first example is just, the book just gives you 2 matrices and we check that one is the inverse to the other. So part 1 of the example is we have a matrix A, which is 2, -5, -1, 3. And we have B equal to 3, 5, 1, and 2. So if you calculate A times B, and if you calculate B times A, so A times B, for example, is 2 times 3 minus 5 is 1, 2 times 5 minus 10, 0, minus 3 plus 3, 0, minus 5 plus 6, 1. Now the other way around, B times A, 3 times 2 is 6. 3 times 2 is 6, minus 5 is 1. 3 times -5 is -15, plus 5 times 3 is plus 15, 0. 1 times 2 minus 1, 1 times 2 is 2, minus 2 is 0. 1 times -5 plus 3 times 2 is 1. So therefore, this matrix is the inverse of this matrix, or the other way around. Okay, so the whole point is now you can ask, if you have never seen this before, actually here finding the inverse is not so complicated, but we will do this in a moment. In the moment, just that drops out of nowhere again. So this is just checking. If I have to check that A and B are inverse, I multiply A times B, and I multiply B times A. If I get the identity matrix each time, I know that B is the inverse of A and A is the inverse of B.
So, Professor, could we also have implied that A is inverse of B, like instead of B is
Yes, yeah, that's what I said before in the previous remark. The definition is symmetric. If B is A inverse, A is also the inverse of B.
Okay.
Yeah. The only thing which, if you have never seen anything like this, is how in the world did they come up with B? No. That's something you will see in a moment. It's actually not so difficult. This is just an example where we just check B is the inverse of A, or the other way around. And now the next thing is about that things get more complicated with matrices compared to with real numbers. So if you make the matrix A, which is 1, 1, 1, 1, and now the question is, can you find an inverse? So the question is, can we find an inverse matrix? No. And then we take this matrix and multiply by B and try to figure out what is B11, B12, B21, B22. So now we multiply A times B, which is 1, 1, 1, 1, times B11, B12, B21, B22. And the question is, can we make it that we get this, no? Can we arrange this? Now, when I multiply this, what do I get in the upper left if you multiply this matrix with this matrix? Can someone tell me what goes in the upper left?
B11 plus B21.
Yeah, correct. You'd multiply the first column here with the first row here. What goes in the lower left? Now, first column times second row.
B21 plus B22.
No, first column, try again. Also, first column times second row of A.
B11 plus B21?
Yeah, it's B11 plus B21. So it turns out it's the same thing, no? Yeah, and I don't even care what's here, no? Now we see, okay, what do we actually like? We like this to be 1 and this to be 0, but it's the same.
So it's impossible, right?
So that is impossible. So what does it mean? This matrix has no inverse, no matter what you do. So this is impossible. Possible. So A has no inverse matrix. So that shows you the situation even for 2 by 2 matrices is more complicated than for numbers. This is a wonderful matrix, has no zeros in it, but it has no inverse. So, so that again is a point where the world becomes more complicated to us. No? So matrices don't commute. AB is not BA. AB equal to 0 doesn't mean that A or B is 0. And 0 doesn't mean that A has an inverse. So these are differences between matrices and numbers. So you have to be a little bit careful when you work with matrices instead of numbers. A lot of things are the same. That was our first property, list of properties today. But some things are different. Okay, so this is actually bad now, that it's not so easy to figure out if a matrix has an inverse or not. Then now come some good things. For example, is it possible that a matrix has 2 different inverses? It turns out that's impossible. If a matrix has an inverse, then you have an inverse matrix and there's no other matrix which is also an inverse. So this is something what we call the inverse of a matrix, if it exists, is unique. So if you have one, that's it. There's no other one. And that's our next result.
Professor?
Yes?
How did you know that we wanted to get the 1001 at the bottom? How did
Because that's the definition of an inverse, no?
Oh.
A times the inverse must give me the identity matrix.
Oh, okay.
If I have, if there is an inverse. No, it turns out there is no inverse here, no?
Okay, thank you. That clarified it for me.
Yeah, always ask. Also, yeah.
Professor,
Yeah?
can you just assume that if you have the 2, -5, and then on the V matrix is 5 and 2, can you just assume that if it has the same order or the same numbers, that's an inverse instead of doing the processing itself? I don't know if I explained myself.
You mean going from here to here is always in the same way?
Correct. Like, you know how you have the 2, -5.
Yeah, you flip these 2 and make these negative. Yeah, actually it turns out this is another result we have in a moment. Yeah, that's for 2 by 2, that's always like this. Mm-hmm.
So in that way, you don't really have to do the process, correct?
Yes, also for 2 by 2 matrices, you will see in a moment that's very easy to find the inverse.
Okay, thank you.
It turns out there's no formula like this for 4 by 4. No?
Okay, thank you.
But 2 by 2, it turns out you're right. Turns out it's not very difficult. Yeah.
Thank you.
Anything else about this? Okay, so again, these are actually more, especially this one is a negative result. Negative in the sense it means the world gets more complicated for us. Now comes the result, several of them, which tell us, oh, it's not so bad. Certain things are still true. So in your book, when you look, this is theorem 1.44.